All right, 7.2. So I've done a little bit of a different thing I'm trying with these notes now, where I just type up some of the things originally. So just make sure you still write these things down in your notes so you have them, but this way it's a little bit more legible, and I can shorten up the videos a little bit for you guys too. So we're covering section 7.2, which is all about talking about rate of change and how that relates to the slope of a line. So in 7.1, we started visualizing those lines by graphing them using a few points. Okay, and today we want to talk about a very important part of those lines, which is rate of change. So we need a definition for rate of change to understand what it is. The rate of change is equal to the change in the output over the change in the input. That's kind of our general definition of rate of change. Okay, directly related to slope, and we'll put the definition to slope to this here in a second. What I want you to remember here, since we're finding the change here, is we want to remember, oops, if I can spell remember correctly, right? There we go. We want to remember that change, back from chapter 1, change is always equal to the final value minus the initial value. So just keep that in mind as you are doing these next examples where we're going to find rate of change. Okay, so let's look at this first example here and try and apply that definition. In this first example here, we're saying, okay, an airplane's altitude increases steadily by 10,000 feet over a 5-minute time period. And we want to find the rate of change of altitude with respect to time. So actually, instead of highlighting all of that, let's highlight the important part. So our rate of change is going to increase steadily, okay, by 10,000 feet over a 5-minute period. That's the really important information right there. And if we want to find the rate of change in altitude with respect to time, that's helping us understand what the output and input are going to be. So over time, our altitude is changing. So that means for us, our output is altitude and our input is time. So we want to find the change in altitude with respect to time. So over the change in time. So we want to think, okay, what's our final altitude then to find the change in altitude? Well, we don't have a final and initial here. We just actually know that change. We know that we increased by 10,000 feet in altitude. So that's a change of a positive 10,000 feet. And I like to keep those units with my numbers so that I know the units of my rate of change in the end. So here we were just straight up given that change and didn't have to think about the formula final minus initial up there. Okay, and same thing for time here as well. Time increased by 5 minutes, and that's where we increased by 10,000 feet. So this is where now we're going to find our average rate of change. We know that in 5 minutes we increased by 10,000 feet, but we want to find that average rate of change, which is going to be how many feet do we change per minute. So if we take 10,000 divided by 5, we will see that that number is 2,000. And then we see the units right here, feet, and whenever we divide, we say that is per minute. So we read this or say this as feet per minute. So what we're seeing is that average rate of change. On average, the plane's altitude increased by 2,000 feet per minute. Okay, so we get that average rate of change when we know the overall change. Let's try it again. Again, as we're reading this, we're thinking, okay, we need to understand what's going to be the output and what's going to be the input. So in this example, we have that the temperature decreased steadily from 62 to 50 degrees from 6 p.m. to midnight. And we want to find the average rate of change in temperature with respect to time. So notice that wording is very helpful, right? Altitude with respect to time meant that altitude was the output and time was the input. Here, temperature with respect to time. Temperature is going to be changing over time. So our output is going to be temperature. So we want to find the change in temperature over the change in time. And now notice this time we don't know that change in temperature. We just know that it changed from 62 degrees to 50 degrees. So we're going to use that fact that we need to take the final temperature minus the initial temperature. Make sure you take the final temperature minus the initial temperature here. You'll see that will be a negative temperature, showing that it did in fact go down from 62 to 50 degrees. Okay, 62 to 50 degrees is our unit in the numerator. And time, it's changing from 6 p.m. to midnight. So think about that. This is 6 p.m. and midnight is 12 o'clock. Okay, so we can think about those times because they're both PMs. 12 o'clock minus 6 o'clock, that's hours of time, right? Every time we report time, that's in hours. And these two work because, again, these are both PM, right? This is 12 p.m. midnight. Okay, so I find that the difference in the temperature went down 12 degrees in those 6 hours that it took to get from 6 p.m. to midnight. So in our final answer here, we divide -12 by 6 and we get a number of -2, and that's degrees from the numerator per hour. So I know that it changed by 12 degrees in 6 hours. That's an average change of 2 degrees every hour. We're getting that average rate of change. See if you can try this next one. This one says the number of employees declined, so we know that rate of change should be negative. It declined from 58,000 in 2014 to 41,000, I'm saying these numbers wrong. 583,000, there we go, in 2014 to 491,000 in 2018. Okay, the number of employees has changed over time. So we want to find the rate of change in the number of employees. Now, a lot of the time, notice that this time I didn't put in the time thing. Sometimes that's assumed. Okay, if we're finding the rate of change in the number of employees, we're going to find that rate of change over time. So again here, employees is changing with time. So we want to find the average rate of change by taking the change in the output, which is employees, over how much time is passed, changed in time. Remember here, final minus initial. The final amount was 491,000 in 2018. So final number of employees minus the initial, final year minus the initial. The initial was 583,000 employees in the initial year of 2014. So notice your units here are going to be employees, and this time our time is in years. We're going to see that decline now, getting that negative number in our numerator. If you take 491,000 minus 583,000, you will get negative 92,000 divided by 4, 2018 minus 2014, 4 years have passed. So we can see we lost 92,000 employees over 4 years. That's an rate of change, if you divide those two, of negative 23,000, and what's your unit? Employees per year. So we know how many we lost in 4 years. That average rate of change then is 23,000 per year. Okay, another thing this is really good for is if we know how many classes cost a certain amount, and we know a couple different points there, we could find how much it is per class. That's what we're going to do here. So we know 12 karate classes is $158, and we know 20 karate classes is $230, and we want to figure out, okay, what's the rate of change of cost with respect to the number of classes? So we're trying to find the cost per class. Again, this wording is helpful. Cost with respect to the number of classes, this is always your output over your input. So we're trying to find the change in cost depending on the change in classes. Okay, so we have two different points here. The second point we know, just make sure you line these up, right? What's your change in cost? So we ended at 230, we started at 158. So 230 minus 158, our unit there is dollars, over change in classes. We ended at 20, we started at 12 classes. So that will give us 230 minus 158 is $72. So it went up $72 for how many classes? 20 minus 12 is 8 classes. So that must mean that we are paying $9 per class. And that is our rate of change. And that final rate of change, right? It helps us a lot. It's a very important statistic, a very important number to know for the cost per class of these karate classes. Okay, so rate of change has a lot of applications when it comes to real life scenarios, right? These changes over time or these changes over different things we'd like to know, like cost per class. Now, rate of change when we're thinking about a line is called the slope. So the rate of change when we start talking about a line is slope. So slope, the definition here is that it is the rate of change. And this time when we're talking about a line, the output is y with respect to the input to x. So this means we need to have the change in y over the change in x. And that we write as y2 final y minus initial y over final x minus initial x. So final is the second point, initial is the first point. And that is our slope formula, and slope often gets the variable m. Okay, so m is what we use to represent slope. Remember, we use things like x bar and a capital M to represent mean and median. We have a lowercase m to represent slope, which is always the second y value minus the first over the second x value minus the first. So we want to apply this definition of slope. So notice here we need 2 points to find the slope of a line. So here I've given you 2 points, and we're going to actually use then those 2 points to graph the line. But the first thing we're going to do is understand what that rate of change in the line is. What is the slope? So what's really helpful here is to think about labeling these points. This one, 2, 3, is the first point listed. So I'm going to give it the subscripts of 1, x1 and y1. The second point listed, I'm going to say is x2 and y2. Okay, so then all we have to do is plug these numbers into our formula. So our formula is y2 minus y1 over x2 minus x1. So in this case, y2 is 5, y1 is 3. So 5 minus 3 over x2 is 8, and x1 is 2. Notice 5 and 8 will always come from the same point, and 3 and 2 will always come from the same point. So that's why it's important to label those points and keep track of those numbers, and label your points from the beginning to make sure you get that order correct. Okay, so a slope then that we get, 5 minus 3 is 2 over 8 minus 2, which is 4. And slope, we always want to give that, sorry, 8 minus 2 is not 4. 8 minus 2 is 6. There we go, that's a better slope. Slope we always want to give as a simplified fraction. So do not put 0.33, that's not accurate, that's a rounded number. The final answer here for slope is always the simplified fraction, which is 1/3. So what we're going to do is graph this line. Now, so far, I at least know 2 points on this line. So let's graph those 2 points on a grid and see if we can visualize from just those 2 points what a slope of 1/3 looks like. So I want the point 2, 3. So 2, 3 would be right about here. Okay, and the point 8, 5 right there. Okay, so I'm going to graph the line between those 2 points. Now, before I simplified slope, I had 2/6. What you're visualizing there with slope is that means I went up 2/6 here, 2 and 6. Now that's simplified to 1/3 because I can also go up 1/3 and see there's another point on my line right there by going up 1/3. Okay. Notice also, I kind of glazed over this, but I just graphed a line using only 2 points. In fact, 2 points, and you will see that relationship of the line. I had no problem figuring out, okay, to connect those 2 points, I have a line. So even though before we were using 5 points to get a good picture because we weren't sure that the equation was a line, anytime we have a line, you only need 2 points to graph a line. Okay, so that makes it pretty easy to graph this line since we were giving those 2 points from the beginning and visualizing that 1/3 slope there. Also notice this is a positive slope, so we have that increasing line. It's going up from left to right. Okay, so let's see what another slope might look like. Pause this and see if you can find the slope of this line and graph the line to visualize what kind of slope we see. Here, you should get y2 again minus y1 over x2 minus x1. This is x1, this is y1, this is x2, this is y2. So y2 was -4, y1 was 4. So minus from the equation and then 4. x2 is 7, and now be careful with this x1. There's a minus from the formula and a -1 I have to plug in for x1. Anytime I'm plugging in a negative number, I like to put it in parentheses so I can differentiate the negative from the formula for slope from the negative for the value that I'm plugging in. Okay, so keep those parentheses there. So what this means is we have -4 minus 4, that's -8 over 7 plus 1. These come together, 2 negatives become a positive, over 8. So my final slope, simplify that fraction, is -1. Okay, so I go to graph this line, and I just graphed the 2 points that I have from up here. Make sure we can see that. So -1, 4 is right here. And then 7, -4 is down here. Okay, so I graph, well, let me see if I can do a better job of that. I graph the line between these 2 points, getting that as straight as possible. And what I'm visualizing here is that original change. So from one point to the other, I go down, I change in y by -8, and I change in x by +8. So -8 is your change up or down, it's your change in y, and +8 is your change in x. Now you're visualizing this -1 here. Think about it as -1 over 1. From any one point, you can also go down 1, right 1, down 1, right 1, and that's defining the change between every point we see on this line. Okay, so we can also think of slope as rise over run. We're going to change up or down based on the numerator number, and we're going to change left or right based on the denominator number because it's change in y over change in x. Okay, this is also a good visualization of a negative slope. Okay, so here we're visualizing, oops, let me see if I can get that line back. Let's just undo that. There we go. We're visualizing that negative slope. The blue line is decreasing from left to right. So we're visualizing a new type of slope there, which is negative slope. And my thing just kind of reset there. There we go. Okay. So there's two more types of slope, positive slope versus negative slope. They work just the same way. Every slope is still going to be rise over run. We have two kind of special slopes. Remember those two special lines from the first section 7.1 with horizontal and vertical lines? Well, we're going to see some special slopes come out from those types of lines. Okay, so just see if you can calculate the slope between these 2 points first. Remember, y2 minus y1 over x2 minus x1, and something interesting is going to happen in this one and the next one. Here, when you take your y's, we'll have 3 minus 3. Both of our y values are the same. X2 is 4, x1 is 2. So we get 0 over 2. Now you can always use your calculator to help you out to remember this, but 0 divided by anything is 0. So let's plot these 2 points at 2, 3, and 4, 3. And we visualize there then that it must be that a horizontal line has slope 0. And that makes sense because 0, think about 0 being 0 over 1, it doesn't change in the y direction, but changes by 1 in the x direction. Okay? So a slope of 0 is a horizontal line. Now, something a little bit different is going to happen with those vertical lines. So see if you can see why this is a vertical line here and calculate what that slope would be. So you should have taken 4 minus 3 over 2 minus 2, right? y2 minus y1 over x2 minus x1. But this time you get 1 over 0. And if you try and plug that into your calculator, you'll get an error. You cannot take any number and divide by 0, not even 0. Okay? So if we have a 0 in our denominator, then this is what we call undefined slope. So we want to visualize what kind of line has undefined slope. So plot those 2 points at 2, 3, and 2, 4. And you'll see there you get that perfectly vertical line. So vertical lines have undefined slope. That's what we call it. I always remember the difference here between horizontal and vertical. As horizontal, you're not going up or down, so you don't have positive or negative. You're right in the middle between those at 0. And vertical, you're going perfectly up and down. You couldn't climb this slope. It would be impossible, right? So that's undefined. That's kind of how I remember the difference between the two. Okay, so that's our 4 types of slope, and that helps us understand lines here. Okay, so we're going to look at some more examples here in a second, but I want you to understand increasing is a positive slope, decreasing is a negative slope, and horizontal lines have slope 0 and vertical lines have undefined slope. Okay, so make those notes for yourself. All right, a couple other things we want to be able to do from this section. Let's see if we can reverse this. So see if you really truly understand slope here. Given a line, can you find slope? Remember, we just need 2 points to find the slope. So you're visualizing where are 2 points on this line. So here's a point you could use that clearly crosses some crosshairs. Here's another point you could use. Here's another point you could use. Okay, you go to the left. You want to find the points that clearly cross on some crosshairs. And then what you're going to do is you're going to calculate that rise over run, that change in y over the change in x for this particular line. So start at any point. It doesn't matter where you start, but wherever you start. So I'm going to start here at this point up here, let's say. And I'm going to go to this point down here. So I'm going to change in y first. I go down 3 units and I go left 2 units. So that's a rise of -3 and a run of -2. I see that this line is increasing, so it should have a positive slope, which I get because the two negatives will cancel, and I get a slope of 3/2. Now I want to point out, I'm going to kind of back up on this. You can use any 2 points that you want. So let's say I hadn't found those 2 points, okay? Let's go back here and say, originally when I looked at this line, I knew I had to find 2 points. Let's say I found the two furthest apart, right? Let's say I saw this one up here, and then I saw this one down here. And that's totally fine. That's so long as you're changing in the y direction first. So if we start at this top point up here, then I have to go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 units. I think I counted that right. And then we got to go left 1, 2, 3, 4, 5, 6, 7, 8 units. And that's all right. So I changed in y by -12 and I changed in x by -8. Remember, slope is always the reduced fraction. If you reduce this fraction, 4 comes out of both, right? So if I take 12 divided by 4, I get 3. If I take 8 divided by 4, I get 2, and the negatives cancel. So what slope do you end up with? The exact same slope as before. So what you're saying is that from any 2 points, I can go up 3, right 2 to get to another point, up 3, right 2 to get to another point, okay? And we're seeing that slope of 3/2. So every time, in order to find the slope of a line, you just need to indicate 2 points, change in the y direction, then change in the x direction. If you do it this way, you can change in the y direction by going up, and then change in the x direction by going right. That's fine too, okay? Just make sure you change in y, then change in x, and simplify your fraction. Last one I want to look at here is the whole reason we started doing this, right? Well, the first place we saw this was when we had models of linear equations, okay? So look at this, we have some data, right, that's being modeled by this line right here. So what I want to do is think, okay, well, here's a line. I could estimate the slope of this line using the exact same method we did before. I see again that it's increasing, so my double check at the end is that I should find a positive slope. And if I want to estimate the slope of this line, I need to find 2 points that I can pretty easily tell are on the line. Now, I'm not seeing it cross at nice crosshairs here, so we're going to have to estimate a couple of points on this line, and that's all right. So I'm going to find ones that are at least close. Like this one looks like it pretty closely does the middle there. So I'm going to use this point, which would be at 2,000. And if I'm reading the scales, right, this one's at 2,000, and then halfway between, let's see, halfway between, let's put the commas in there, 1,500,000 and 2 million. Halfway in between those 2 points would be 1,750,000. Oops, need another 0 there. All right, and then we can find another point. Let's see here, that would be good on this line. Again, you can use about anything. This one's close to halfway too. I would go a little bit above halfway there. So we could use that point and drag that over. And this one I would estimate to be definitely 3,000 square feet and just above halfway between 2 million and 2,500,000. So I'd probably go 2,300,000 there. Okay. And once we have 2 points, we can calculate the slope. Now this one isn't easy to do on the graph. I can't really go up and over all that easily. So once I have those 2 points estimated, let's just use the formula for slope. Okay, so I'm going to rewrite those points down here. I'm using my 2 estimates, 2,000 and 1,750,000. And my other estimate at 3,000. And let's see, I made that estimate at 2,300,000. Just double checking those points there. Yep, that makes sense. Okay, so this would be my x1 and my y1. This would be my x2 and my y2. And I would just take 2,300,000 minus 1,750,000. Now, if your estimates are a little bit different, if you tried this before watching, it's okay that your slope gets a little bit different. Oops, I had something on my screen I was trying to get off there. But your slope should still be close to mine in the end, okay? So 3,000 there minus 2,000. We end up here then with taking that subtraction. Doing that in my calculator real quick, and you would do your subtractions as well. I get a difference of 550,000 in my numerator over 1,000 in my denominator, and that gives me 550. Now, that's a good slope, but I want to know, what does it mean in this situation? Okay, so I have to go back and understand what my variables are here. So let's go back. Read the titles. This is square footage versus sale price of a house. So we have a bunch of data points we collected where certain houses were a certain square footage and then they sold for a certain price over here. Okay, so what did I do? Change in Y over change in X. So change in Y, my unit up here is dollars, my sale price, right? My unit down here is square feet. So this is a difference. It's going up by $550 per square foot. Okay, so we're finding that average rate of change in price, sale price of a home per square foot. So you can always find those units, find what it means in the situation by just taking the unit of the Y per the unit of the X. So now our model makes sense. We're estimating the slope of that line to be 550, which means we're estimating that rate of change to be $550 per square foot for this data. So again, that linear model gives us a rate of change to this data. Without that linear model, we wouldn't have been able to come up with a rate of change that made sense for this data. Those linear models are very helpful, and now we know that a component of those linear models, the slope or the rate of change, is also very useful when applying a linear model. Okay, so give those a chance in your homework, and again, reach out to me if you're stuck and you have questions. All right. You will also have an activity on this section that I'll have you turn in Talon. You do not have an activity for 7.1, so make sure you check out that activity and give it a shot as well. All right, guys, I'll see you for 7.3 and hopefully at our Zoom help sessions.